Hello, everyone. My name is Kwame Ade. I'm the founder and director of the Center of Operations Research and Data Science, CORDS. I double also as an assistant professor at the Minnesota State University, Moorhead. In today's video, I will talk about random forest model and illustrate it using the R software. So when we say random forest model, what is it? The random forest model is an ensemble machine learning algorithm, or in some parlance, it is called algorithmic artificial intelligence model. And what it does is that it builds a collection of decision trees and combines their predictions to improve accuracy and robustness. So when you are running the random forest model, what you are doing is that you are training each tree on a bootstrap sample from your original data. And what the algorithm did for you was that it selected a random subset from the original data with replacement. Now, at each split in the tree, the random subset of features is rather considered instead of using all the features. Now, the random forest can either be used for prediction of classification outcomes or regression outcomes where your outcome variable is a continuous variable. So let's look at this diagrammatic example here. So when you look at this diagram here, this is your original data or your training data. And the training data, we are seeing several bootstraps going on here. And this bootstrap, of course, because there's bootstrap with replacement, you are seeing, for instance, A4 observation, A4 is being read twice here. So there's replacement going on. Now, once this bootstrap is performed, then the trees are assembled to be able to give you your average prediction. So in decision tree 1, it tells me that the outcome is class 1, or the vote will be class 1. And as a matter of fact, looking at these 4 decision trees, what we are seeing is that more of them show an outcome or a prediction of class 1. So then we can say that the majority will vote class 1. Now, this is an example of random forest being applied to a classification prediction or a classification model. Now, let's delve into R and look at an application for forecasting of a continuous variable. So, when we come here in the codes, what you see is, of course, the most important package here is the random forest package. But because I perform a number of data pre-processing steps, so you need these other libraries too. So try and install them if you don't have them installed already. So what am I trying to do here? I want to forecast Canada's exchange rate or Canada's currency. So I'm trying to forecast the Canadian dollar to the US for the future using a random forest. Now, for me to forecast it, I'm trying to use other currencies as the feature. So the other currencies I'm using in my data are the Chinese yuan, the euro, the Japanese yen, and the British pound. So I'll, I use the read Excel because my data is an Excel data. But I'll just call in all my libraries to ensure that I don't have any issues when I run them. So now I call in my variables from their Excel, and then I don't see any errors. So I think I'm in good shape. And I try and I merge all of them by date. And again, and of course, I decided to use a sequential modeling merging because I just needed to be sure everything is merging right. But definitely you can merge everything together at once using one line. Then the next thing I do is I try to plot these trends here. These are the trends for the variables. So when we look here, we see that the UK pound to the US dollar over time has exhibited some level of volatility. We come here, we see that the Japanese yen, despite volatility, has seen an upward trend, especially in recent times. The euro shows a high level of volatility, even though it hasn't reached its peak again since this period. And then the Chinese one definitely shows high level of volatility with a bottom trough here. In the Canadian dollar, which we are trying to predict in recent times, has seen an upward trend. So these are the trends of the currencies that will be used in our model. So then because I mentioned that I'm trying to use the 4 other currencies to predict or to forecast the Canadian dollar, I want to plot a correlation amongst these 5 currencies. So I take out the column 1, which is my date column, and then I have the 5 currencies and I plot a correlation for these 5 currencies. Now, there are several ways by which you can plot correlation. I use the core plot here and I show 4 different ways by which you can plot your correlation metrics, and you are free to choose whichever one you want, or if you want any other one that is not being illustrated here, you can definitely do that. So over here, the correlation amongst the variables is being shown, or correlation between the variables is being shown by intensity of color and then the size of the shape. So on the diagonal elements, I expect a positive one or a perfect correlation. So it's easy to be able to see here. And the legend here tells me that a deep blue is for 1, which is a perfect correlation. And because it's the variable against itself, so definitely there's going to be a perfect correlation. But however, when you look at the other correlation values, the color is a bit tricky, right? Because when I look at this color and I see the size here, I am in limbo as to whether it's 0.6, below 0.6, or slightly above 0.6. So I'm mostly not comfortable with this type. And of course, this is also one that you this time it's the intensity of the color alone that determines your correlation value. The one I kind of feel more comfortable with is this particular one where you have the actual number. This may not be very fanciful, but it does the job for you. And of course, there are other correlation illustrations that will combine this and the color and size. So this is for this particular one, which is line 38. And of course, the first one is also shown here where I ranked or I presented them based on alphabetical order. Okay, so now that we've seen the correlation amongst the variables, another thing I want to use as a feature in this model is I want to use the lags of the Canadian dollar. So for me to use the lags, or for me to create the lags, I change the Canadian dollar variable into an STS file. So once I change it, I then go ahead and I create 12 flags. I'm using 12 flags as the standard, even though there are ways by which I can select the optimal lag. However, because that is not the focus of today's video, so we'll just use the standard of 12 flags. So once I create this, I now go and merge. So because it's an STS file, what I do is I convert it back into a data frame using line 54. Then I now merge the lags I created to the original data. So in essence, this data I'm calling final data here is going to have all the features that I'm going to use to help forecast the Canadian dollar exchange rate. And then I just want to make sure I do not have non-availables as rows in there. So then now that I have my data well processed, I can go ahead and do my forecasting. But one thing I want to do, because I want to test the accuracy of my model, is I want to split my data into a training data set and testing data set, as we typically do in machine learning. So the training is what the model would have seen, and then the testing is what the model has not seen, and that's what it's going to predict, and we see if it's at the level of accuracy. So I just arbitrarily picked a split of 80% to 20% of training and testing. So that's what you see in line 66. So once I do that here, I can go ahead and run my random forest model. Of course, recall that I called in my random forest library previously. So then that's all good here. So in line 73, I'm running the random forest model and I'm calling the model I'll run as rf underscore model. And I'm using all the variables in the data set. And the data set is the training data set. So it means it's going to have all the four other currencies, exchange rate to the US dollar, and then the 12 lags of the Canadian dollar. Then I'm using 100 as my number of trees. In some work, 500 is used, some you see 1,000 and some you see 10,000. It's dependent on the size of your data and then the accuracy of prediction, number of variables, and so on and so forth. But I'm just using 100 as the number of trees because, of course, that's going to be fast for this illustration. And the data I'm using is also a small data. But we will definitely even look at it and see if we would have gained by using more number of trees. So first, I run this. And then when I run it, I print the model outcome. So when I print the model outcome, I'm seeing that the percentage of variance explained is 98.89, which is very high and very good. And then the mean of squared residuals is very, very low here. That's about 0.0000276, thereabout. So that's what I'm seeing here. Now, the first question I want to ask is, could it have been better? Now, could it have been better? Then it means I'll just run line 76 and then I'll plot the number of trees and the mean square error and see. I just use line 75 to ensure that my plot fits within the frame and it is reset. So I plot this and this is what we are seeing. So we see that there's a sharp decline as you increase the number of trees. Then from 40, or let me say 60 onwards, we really do not see any reduction. Now, bear in mind, our goal is to have the least error, right? So assuming the error is 0, it would have been good. But we see that it goes so low that you begin to wonder that from this point onwards, if we had increased the number of trees to 500 or say 10,000, would we have seen any high level of reduction for the computational effort and time we would have wanted? And always bear in mind that in machine learning or artificial intelligence, parsimony is always key. So you want to choose the simplest model that will do the job as well as you want for you. So based on this, I really do not see that you would have had any huge improvements if I had used 500 trees. You can try it on your own and see 500 trees, 1,000 trees, and see what level of accuracy you would have had. Now, the next thing I want to do is I want to see the variables that are important in my prediction. So I'll just plot, I'll just run and see which variables that are important. So I see that the lag data had the highest level of purity or node purity. So it goes to show me that the lag data had the highest level of significance on forecasting Canada's exchange rate. And that is true because that is the most related. There are several other beta variables we could have used, but this is for the sake of illustration. We see that the Chinese one was also highly related to forecasting the Canadian dollar. Now, I can do a variable importance plot, and then we see. So we just see this as the most important and so on and so forth. So this looks kind of nice, and we are seeing the variables that are important. Now, I definitely you can also do some more decision, plot the trees, but notice or bear in mind that it will be very clumsy if you did plot the 100 trees here, right? So I just decided to plot one level of the tree, and then we see. So it's showing us the two variables here, their importance being shown here. So recall that when we defined random forest, we mentioned that it combines different trees. So the question you want to ask yourself is that if you had used just one tree, how different would it have been from using the random forest? So I ran this model here where I just perform only a simple or one tree. So I use the R part. So try and install that package if you do not have it. So once I use the R part, I try to also plot it and see. So with this decision tree, this is how it looks like. And this, of course, the R part allows me to do a more fanciful plot than the random forest. But that is not our major concern, right? We are seeing that the lag data is the most influential, but that's not our major concern. Our major concern is prediction accuracy at this point. So why don't I perform the predictions and see the level of accuracy? So in line 99 and 100, I perform predictions on the test data for the random forest and then the single tree respectively here. So once I do that, I then go ahead and plot their and calculate their root mean square errors. So let me calculate their root mean square errors using line 104 to 108. So these are their root mean square errors. So when you look at the root mean square errors, for the random forest, it is 0.02, and that is lower than using just one single decision tree because you are seeing that that is 0.03. And of course, when it comes to prediction with root mean square errors or residual errors, you want the lowest. So of course, we now see that the random forest performs better than the single decision tree. And I can definitely do some plots of our forecast and we see. So in this particular line of code from line 112 to 116, I plot the forecast here. So this is using the random forest forecast. And this is how it lines up. And don't forget that the split was 80-20. Then now, what I try to do here is I try to overlay that of the single tree and see how it's going to look like. So this is how the single tree looks like. So we see it's not very close or it doesn't even look very good. Then I combine the two for just visualization, and then we see it here. So, well, even though it doesn't look like the random forest is that close, at least it is following the trend better than the single decision tree. So we've addressed the question, if we had used a single tree, would it have been better? The answer is clear, no. If we had used more number of trees, would it have been better? The plot I showed doesn't seem like it would have improved by much, right? So then the next thing we can say is, would we have seen a significant difference if we used different splits? So for instance, I mentioned 70-30, 50-50, 60-40, and so on and so forth. Would it have been better? So